Hi Year 12, this is the second video for the topic of complex numbers. In this video we're going to look at different representations of complex numbers. So last lesson we learnt about the complex number system and operations with complex numbers. So hopefully you remember how to add and subtract, multiply and divide, how to make the denominator real, and how to do the square root of a complex number. So this is what we're going to look at in this video. Geometrical representation of complex numbers, in particular vector representation. Then we're going to look at polar form, which is also known as MOD-ARG form, and then exponential form, also known as Euler's formula. So complex numbers are represented on a plane, which is also called an Argand diagram. And the x-axis represents the real part of the complex number, and the y-axis represents the imaginary part. We can represent it as a point, like the point A, B, or we can represent it as a position vector from the origin. So have a look at these complex numbers. They're represented by vectors drawn from the origin. This complex number, minus 3 plus 2i, would be represented by the point minus 3, 2. This one here, 2 plus i, it's got coordinates 2, 1. What about this one, 3 minus i? Coordinates are 3, negative 1. And then finally, minus 2i has coordinates 0, negative 2. But recall that vectors don't have to start at the origin. They're free to wander anywhere. If a vector starts at the origin, it's called a position vector. Now in this case here, the vectors OP and AB both represent the complex number 2 plus 3i. However, point P represents 2 plus 3i, but point B does not. Now we need to revise some vector operations because they're going to come in handy. Firstly, addition of vectors. The sum of two vectors is the combined displacement of the two vectors, and it is found by applying the second vector from where the first vector finishes. So let's pick up our second vector and apply it to the end of the first vector, and we're going to go all the way from the beginning of the first vector to the end of the second one. And there's the addition of u plus v. Remember that a negative vector will head in the opposite direction to the positive vector. So A and negative A are parallel. They are equal in length, but they are opposite in direction. So you can see that the arrow faces this way for this vector and faces this way for this one. And we could say that BA is the negative of AB. If we want to subtract one vector from another, we add its negative. So here I've got the vectors u and v. We're going to take the negative of v, so turn it around, and then apply it at the end of vector u. Combined displacement is that red vector there, u minus v. Now that's one way of subtracting vectors, but there is a shortcut, and this method can be really useful when we're doing geometrical proofs with vectors. So we can recognize the subtraction of vectors when two vectors start from the same point, like here. The resulting vector, if it points towards the u, this is u minus v. If it points towards the v, then this is v, take away u. But don't take my word for it. Go and play with this and make sure this makes sense to you. Multiplication of a vector by a scalar will change the magnitude of the vector, but it doesn't change the direction unless the scalar is negative or 0. So here we've got a. If I add another a and add another a, I've got 3a. All right, let's return to this question that we looked at before. If z1 is equal to 3 plus I and z2 is equal to 1 plus 2i, represent z1 plus z2 on the complex number plane. So one thing we can do is just add those together. We know how to do this. We add the real parts, we add the imaginary parts. So z1 plus z2 is 4 plus 3i. Or we can do vector addition. So there's the two vectors, and finding the combined displacement, we get the same answer, 4 plus 3i. Okay, here's an important example. If z is equal to 1 plus 2i, show iz, I squared z, I cubed z, and I to the power of 4z on the complex plane. So here they are. Let's have a look at them. Here's z, 1 plus 2i. If I multiply by I get minus 2 plus I. Multiply by I again, I get minus 1 minus 2i. multiply by I a third time, I get 2 minus I, and then multiply by I a fourth time, I'm back to the beginning. Now have a look at that for a minute and see if you can figure out what's going on. Okay, here it is. Multiplying by I is equivalent to a quarter turn anti-clockwise about the origin. And this is a really important fact. Here's a t-shirt from the 1990s. You can tell it's from the 1990s because of the phone, but only mathematicians would understand this joke. Sorry, you have reached an imaginary number. If you require a real number, please rotate your phone by 90 degrees and try again. Now let's look at the conjugate and its representation. So the conjugate z is a reflection of the complex number z in the real axis. So here we've got complex number x plus yi. The conjugate is going to be x minus yi. So it just reflects over the real axis. Okay, here's a past exam question. The points P and Q on the Argand diagram represent the complex numbers z and w respectively. Copy the diagram into your writing book and mark on it the following points. The point R representing IZ. So here we've got our complex number Z. And if we want IZ, we are going to rotate that vector 90 degrees anti-clockwise. So there's the point R. The point S representing the conjugate of W. So here's W here. We're going to reflect that over the x-axis. So there's the point S. And then finally, T, the point representing Z plus W. So this is where we're going to do vector addition and find the combined displacement. There's the point T. Okay, let's move on to polar form. The point P, x, y, on the Cartesian plane can be represented by the polar coordinates r cos theta, r sin theta, where r is equal to the square root of x squared plus y squared, and theta is equal to inverse tan of y on x. Now, you've done this before when you looked at the unit circle. So it's just simple trigonometry. If we have an angle of turning and a length along here, then we could say that cos theta is equal to x on r, and so x is equal to r cos theta. Sin theta is equal to y on r, and so y is equal to r sin theta. So we can change the x and y into polar coordinates. Using Pythagoras' theorem, we get this. And just doing inverse tan, or tan theta is equal to y on x, we get this part here. And so instead of writing the complex number as x plus yi, we can write it in polar form, which is r, and then in brackets cos theta plus I sin theta, which we can abbreviate as r cis theta. This stands for cos theta plus I sin theta. This is also called modulus argument or MOD-ARG form. R is called the modulus, it's the length of the vector, and theta is called the argument, it's the angle of turning. And x plus yi is called Cartesian form. We define the modulus of z as the distance of z from the origin. And we write mod z, or we can put the z inside absolute value signs. And it's equal to the square root of x squared plus y squared. Now here's an important point. We don't put the I in. Okay, the I is a placeholder. It's separating the imaginary part from the real part. So the size of the imaginary part is y, not yi. Hope that makes sense to you. Here's another important point. We use the absolute value sign for both scalars and vectors. Now that might seem contradictory, but it's actually the same thing. Think about it. The absolute value of a number like -5 is the size of the number without the direction, so it's 5. The magnitude of a vector is the size or the length of the vector without the direction. See? Same thing. And we define the angle theta as the argument of z. And here's the full definition. Arg z is equal to inverse tan of y on x plus or minus 2m pi, where n is equal to 0, 1, 2, etc. And this kind of makes sense because tan is periodic, and so there is an infinite number of arguments for z. but we define the principal argument as inverse tan of y on x, and we give it a capital A, and it's defined for the domain negative pi is less than theta is less than or equal to pi. Here's an example. Express z equals negative 4 plus 3i in MOD-ARG form. Okay, let's start by working out the modulus. So it's going to be equal to the square root of negative 4 all squared plus 3 squared, which is 16 plus 9, which is 25, and the square root of 25 is 5. Now let's work out the argument. It's inverse tan of 3 on negative 4. Now it's really important that you figure out which quadrant this is in. So don't be tempted just to float this negative up and just do inverse tan of negative 3/4. You'll get the wrong answer probably. So just a quick diagram. Plot minus 4 plus 3i. So it's in here in the second quadrant. What we're going to do is do inverse tan of 3/4 and get the first quadrant angle, and then we're going to do 180 minus that angle. So it's 180 take away 37, which is 143 degrees, and so our answer is z is equal to 5 cis 143 degrees. Here's another one. Find the modulus and argument of z equals 2 minus 2i. Now I'm going to use different notation this time. Mod z is equal to the square root of 2 squared is 4 plus negative 2 all squared is also 4. So square root of 8, which is 2 root 2. Our argument is going to be inverse tan of negative 2 on 2. Quick diagram, it's going to be down in here. So we need to find our first quadrant angle. You can do inverse tan of 1 if you want to, but you should know that that is 45 degrees or pi on 4. And I'm going to give my argument this time in radians. So it's going to be negative pi on 4. Okay, let's go the other way. Express 3 cis pi on 3 in Cartesian form. So let's start by expanding that out. It is 3 outside of cos pi on 3 plus I sine pi on 3. Now going this way is most likely going to involve exact values, so you need to make sure that you are familiar with those. Cos pi on 3. If you need to convert it, that's cos 60. Cos 60 is a half. And sine pi on 3, sine 60, that's root 3 on 2. Now all we need to do is expand this out, and we're going to end up with 3 on 2 plus 3 root 3 on 2i. I'm going to move on to multiplication and division in MOD-ARG form, and I'm going to prove both of these. In Extension 2 Mathematics, proof is really important, and in any test or exam you can be asked to reproduce one of these. So let Z1 equal R1 cis theta 1 and Z2 equal R2 cis theta 2. So our multiplication is R1 cis theta 1 R2 cis theta 2. And let's expand that all out. So you can see how I've got the two brackets there, cos theta 1 plus I sine theta 1 and cos theta 2 plus I sine theta 2. And I'm going to do FOIL to expand that out, which gives me this. Now I'm going to get the imaginary parts together and the real parts together. So I've got cos theta 1 cos theta 2 minus sine theta 1 sine theta 2, and hopefully you recognize this as the expansion of cos and then brackets theta 1 plus theta 2, and then I've got plus I sine theta 2 cos theta 1 plus sine theta 1 cos theta 2, and this is the expansion of sine theta 1 plus theta 2. So we've got that, and now just reducing it back down to this form here, we get this. So Z1, Z2 is equal to R1, R2 cis, and then in brackets theta 1 plus theta 2. And so that means that the modulus of Z1, Z2 is equal to the multiplication of the moduli, and the argument of Z1, Z2 is equal to the addition of the arguments. Let's look at an example. If Z1 is equal to 4 cis pi on 3 and Z2 is equal to 2 cis 5 pi on 6, find Z1, Z2. All right, so we're going to multiply the moduli and add the arguments, like this. So it's pretty easy. We're going to end up with 8 cis 7 pi on 6, but we've got a problem. That 7 pi on 6 is outside the boundaries of our principal argument. You see it's greater than pi, so we're going to have to adjust it. So here it is graphically. We've got 4 cis pi on 3, 2 cis 5 pi on 6 and 8 cis 7 pi on 6. And you can see immediately that this vector here has got a length of 8, and that comes from 2 times 4. And in terms of the arguments, this is pi on 3, this is 5 pi on 6, and the addition of those two is what gives us the 7 pi on 6. So I said before that that's outside our domain for our principal argument. Okay, we want our principal argument to be between negative pi and positive pi. This is greater than pi. A couple of different ways you can do this and adjust it, but probably the easiest way is just to add or subtract 2 pi from it. So I'm just going to write that down for you. Add or subtract 2 pi. And this makes sense because sine and cos are periodic. They repeat every 2 pi or 360 degrees. So here's the rule. If it's greater than pi, we're going to subtract 2 pi. If it's less than negative pi, we're going to add 2 pi. So I'm going to take my 7 pi on 6 and subtract 2 pi, and I'm going to get, here's my answer, 8 cis negative 5 pi on 6. Here's division. Let Z1 equal R1 cis theta 1 and Z2 equal R2 cis theta 2. Okay, so Z1 over Z2 is R1 cis theta 1 over R2 cis theta 2. We're not going to use the same method that we used before, where we expanded it out. We're going to multiply top and bottom by cis of negative theta 2, so the same angle as the denominator. Now we just learnt what happened when we multiply these complex numbers. We add the arguments. So this is what we get. Cis of theta 1 plus negative theta 2 and cis of theta 2 plus negative theta 2. So this is cis 0. All right, this is really important. Check this out by expanding it out and make sure it makes sense to you. But cis 0 is equal to 1 because it wipes out the imaginary part. And so we're actually finished. There it is. Z1 over Z2 is equal to R1 over R2 cis theta 1 take theta 2. So that means that the modulus of Z1 over Z2 is equal to the division of those moduli. The argument is equal to the subtraction of the individual arguments. Here's an example. If Z1 is equal to 2 cis pi on 6 and Z2 is equal to 4 cis pi on 3, find Z1 divided by Z2 in Cartesian form. Alright, so Z1 divided by Z2 is going to be 2 divided by 4, which is a half, cis pi on 6 take pi on 3. Tidying it up, we get a half cis of negative pi on 6. Now, if we were asked for polar form, that'd be the answer, but we need Cartesian form, so we have to expand this out. So we've got a half outside of cos of negative pi on 6 plus I sine of negative pi on 6. All right, which quadrant are we in? We're in the fourth quadrant, and in the fourth quadrant, cos is positive and sine is negative. So cos of pi on 6, which is the same as cos 30, is root 3 on 2, and sine of pi on 6 is a half. And so we're going to get a half outside of root 3 on 2, take away I on 2, which is also equal to root 3 take I all over 4. Here's some special results. I'm not going to prove these, but I suggest that you have a go at proving them. If Z is equal to R and then in brackets cos theta plus I sine theta, then the conjugate of Z is R cis negative theta, and the reciprocal of Z is 1 on R cis negative theta. Here's a couple of identities that are really useful, and you should check out the proofs of all of these. Here's the first one. The modulus of Z to the power of n is equal to mod Z to the power of n, and the argument of Z to the power of n is equal to n multiplied by the argument of Z. If we take the complex number and multiply it by its conjugate, that's the same as mod Z squared. Check that one out, that's really cool. We add complex number and its conjugate, we get 2 times the real part of Z. If we subtract a conjugate from the complex number, we get 2i multiplied by the imaginary part of Z. Okay, last bit for this video. Thanks to Euler, we have another representation of complex numbers, which is Z is equal to Re to the I theta. So this is called exponential form, and it uses Euler's formula, which is e to the I theta is equal to cos theta plus I sine theta. So e to the I theta is equal to cis theta. So let's look at a couple of conversions. Convert the following to polar form and Cartesian form. The first one is e to the I pi on 3. So I'm going to expand that out. We have got a modulus of 1, so we don't need to worry about that. We've got cos pi on 3 plus I sine pi on 3. Cos pi on 3 is a half, and sine pi on 3 is root 3 on 2. So there's our answer. The second one, 2 multiplied by e to the negative 3 pi on 4 times I. Expanding it out, this time we do have a modulus of 2, so we've got to keep that in mind. We've got cos of negative 3 pi on 4 plus I sine negative 3 pi on 4. Now we need to be mindful of what quadrant that's in. It's in the third quadrant, and so cos and sine are both negative there. So we're going to do negative cos of pi on 4 and negative sine of pi on 4. So we're going to get 2 multiplied by negative root 2 on 2, take away root 2 on 2i. And expanding it through, we get negative root 2, take away root 2i. Okay, let's go the other way. Write z equals negative 1 take away I in the form re to the I theta. So we need to find the modulus and the argument. Start with the modulus. It's going to be the square root of negative 1 all squared plus negative 1 all squared, which is root 2. And our argument will be inverse tan of negative 1 on negative 1. Now this is a really good example of why you shouldn't cancel out those negatives there, because you would end up with inverse tan of 1, which is pi on 4, and you'd be in the wrong quadrant. Which quadrant is this in, this complex number? It's going to be in the third quadrant, isn't it? Because both of them are negative. And so what we're going to do is do inverse tan of 1, which is pi on 4, and then go into that third quadrant. So I'm going to do minus pi plus pi on 4, which gives me negative 3 pi on 4. And so our complex number is going to be root 2 e to the negative 3 pi on 4 I. Which brings us nicely to Euler's identity. E to the I pi plus 1 is equal to 0. Now before we go any further, you should go and work this out for yourself and make sure that it is true. So Euler's identity is also known as the God equation, as it shows a relationship between mathematics' most fundamental numbers, and they are e, which is the base of natural logarithms, pi, the ratio of the circumference to the diameter of a circle, I is the imaginary number. 1 is called the multiplicative identity, because when we multiply by 1 we don't change anything. And 0 is called the additive identity for the same reason. When we add 0 to anything, we don't change the original number. Now let's finish off with a past HSC question. The Argand diagram shows the complex number e to the I theta. Which of the following diagrams best shows the complex number negative I e to the negative I theta? All right, we've got a couple of transformations to do here, and we're going to start off by plotting the conjugate, because e to the negative I theta is the conjugate of e to the I theta, and all we do is reflect it in the real axis, so it's down here. Then we're going to multiply that by negative I. Now we haven't really gone through this. Multiplication by I is a 90-degree turn anti-clockwise. Multiplication by negative I is a 90-degree turn clockwise. So let's take that vector here, this conjugate, and we're going to rotate it 90 degrees clockwise. It's going to end up there, so our answer is A. Okay, so that's the end of this video. There's quite a lot in it. It took about 3 lessons to teach in class, so take your time and make sure you really nail the different representations and how to convert between them. In our next video, we're going to look at de Moivre's theorem.